Welcome back to day 2 of transverse shear stress in beams. In the last video, we had this example that was a symmetric I-beam, and we actually went and found the shear stress right here at point A, which was at the junction between the web and the flange. And you guys know that the centroid of this is in the middle. Well, the nice thing about finding the stress right at point A is to find Q, you shade everything above or below that point. So Q is really easy to find because it's just a single rectangle. Q for that purple area, it's y bar prime, a prime. It was 0.16. That took us from the centroid down here to the middle of that. And then we multiplied it by a prime, which was 0.2 meters times 0.02 meters. We got 0.64 times 10 to the minus third meters cubed. Once we did that, we went and we calculated tau A. Tau A was 2.56 megapascals. That was all done last time. What's the harder problem is finding the max stress. Max stress would be down here at the centroid. Let's figure out how we would find tau max. Draw the cross section again. And to find tau max this time, tau max always occurs at the centroid for a transverse shear and beam problem. So we need to cut it at the centroid and shade everything above or below. Let me use a different color. I'm going to shade everything above, and I'm going to end up breaking this up into 2 rectangles, so let me use 2 different colors. To find Q, I actually need to use both of these shapes. As before, Q is going to be y bar prime, a prime. And here's the difficulty. The easier problem is this one, because I can just look at it and the centroid of that purple shape is right there. The problem is I don't know the centroid of this T shape. And usually at this point in these problems, we're getting really tired of finding centroids. So I want to show you a shortcut. First, let's draw on here all of the dimensions that matter. This was 200 millimeters wide. Each of these were 20 millimeters thick. And the web in the middle was 300 millimeters tall. So if I want to find the centroid of the T shape. You remember how we find centroids? It's the centroid of each shape times their area. Add them all up, divide by the total area. I have a big fraction. On the top of the fraction, y tilde for the green area times the area of the green area. On the bottom of the fraction, I'll have just the area of the green shape. Then I need to add to it y tilde for the blue area times area of the blue shape. And on the bottom, I just have area of the blue shape. That is how I would find the centroid of the T shape. And if I make my reference line for doing that, this right here, so that I'm using that as my y tilde for the blue shape and this as my y tilde for the green shape, that will give me the centroid location of the T shape measured relative to the centroid of the whole cross section. So just to find the center of that T shape, let's make our reference line be the centroid of the whole shape. We're going to measure up to get to the center of the blue rectangle and up to get to the center of the green rectangle. Now, how would I find Q for the whole shape? Q is y bar prime, a prime. I just wrote down an equation for what is actually y bar prime. This is going to be the centroid of the T shape measured with respect to the centroid of the whole shape. So this guy right here is equal to y bar prime because I made my reference line the centroid of the whole shape. So that means we can just take this and copy it down. This is y bar prime. What are we going to multiply it by? We're going to multiply it by a prime. What's a prime? A prime is the area of the green plus the area of the blue. Can you see that that's going to cancel? This is a really nice shortcut. What it means is Q for my T shape is going to be y tilde for the green shape times the area for the green shape plus y tilde for the blue shape times the area for the blue shape. This is the same thing as saying that Q for a composite shape like this T is actually equal to the sum of the Q's. We would have already found Q for the green right up here. Already found it. So all we need to do is add to it the Q for the little chopped off rectangle, which I'm calling this blue shape. Let's fill this in. Y tilde for the green, or y bar prime for the green, we got to go from the center of the whole shape up to the middle of the green rectangle, which is 150 plus 10 more millimeters, 160 millimeters, which is 0.16 meters. Y tilde for the green rectangle, or you could think of it as y bar prime for the green rectangle. Then we need to multiply by the area of the green rectangle, which is 0.2 meters, 0.02 meters, 200 by 20 millimeters. This is your A prime or your area of your green rectangle. We need to add to this the Q for that little blue rectangle. So first we need its centroid location measured from the center of the whole shape. The little blue rectangle is 150 millimeters tall, so the distance from that centroid to that centroid is 75 millimeters. So 0.075 meters. That is y tilde for the blue shape, or y bar prime for the blue shape. Then we need to multiply it by the area of the blue shape, which is going to be 150 millimeters tall, 0.15 meters, and 20 millimeters, 0.02 meters wide. So there is A prime, or it's the area of the blue rectangle. We multiply that all out and we get Q max, or Q at the centroid. And it happens to be equal to 0.865 times 10 to the minus third meters cubed. If I want to find tau max for this cross section, we need V times that Q all over moment of inertia times that thickness. Our shear force for this problem was 20 kilonewtons, or 20,000 newtons. We just found Q max, 0.865 times 10 to the minus third meters cubed, and we need to divide it by our moment of inertia. We found that last time, 250.1 times 10 to the minus sixth meters to the fourth, and the thickness is just that little 20 millimeters, 0.02 meters. And it comes out to be 3.46 times 10 to the sixth newtons per square meter, or 3.46 megapascals. And let's compare that to what we got last time, which was right here at the very top of the web next to the flange, 2.56. So going all the way down to the centroid, our stress is quite a lot higher, 3.46 megapascals instead. And there is more math involved, but it's not as much as you might think, because we can simply sum up the Q's. So we had already found the Q for this shape. We're going to add to it the Q for this shape. Let's do a full example now. Instead of being given the shear force, we need to find the shear force. It is a symmetric beam. That's helpful. But here's the problem. This is a problem where we are not given W. We actually have to find W, given that the allowable shear stress anywhere in the beam, anywhere on the cross section, is only 400 psi. So we have an easy cross section, at least. It's simply a rectangle. We'll use that in a minute, but we have to go back to the entire beam, and I don't even know where the shear force is going to be maximum in that beam. When I have a beam like this and I know nothing about where to start, I almost always start with a free body diagram. Starting with a free body diagram, in the middle, I've got my distributed load, which acts over 1.5 feet. I'm going to actually convert everything into inches. So that is 12 inches, that is 18 inches, and that is 12 inches. And I'm not even going to deal with feet because I don't want to have to convert later. So if I look at my distributed load W, however big it is in pounds per inches, you multiply it by 18 inches and you'll get the total force. So we're going to replace that W with an equivalent force equal to 18 inches times W. And I've got at A, since it's a pin, you could potentially have a force in the X direction. You'll probably definitely have a force in the Y direction. B is a roller, so you'll only have a BY. Because there are no applied forces in the X, AX will come out to be 0. If you can see that it's symmetric, you would be able to tell that AY and BY are equal to each other. But if you can't see that, that's fine. You can always use equilibrium equations to figure it out. If we sum moments about point A, they have to sum to 0. And in a counterclockwise sense, I'll have BY, and it appears to be 12 plus 12 plus 18 is 42 inches away. And then acting in a clockwise sense, I'll have minus 18 inches times W, which would be 12 plus 9, 21 inches away, equals 0. BY is going to end up being 9 inches times W. And then if you sum forces in the Y direction, we have AY plus BY minus 18 inches times W equals 0. So AY is also 9 inches times W, or you might have figured that out because it's symmetric. Great, we have expressions for our reaction forces. Up next, I need to figure out what is the biggest shear force anywhere. I find it to be very helpful if we draw a shear force diagram, and we'll draw the bending moment diagram because we should be practicing bending moment diagrams anyway, but the shear force diagram is what's going to be important for this problem. So we're drawing a shear force diagram. What's going to happen is first we're going to go up by AY, which is 9 inches times W. So we're going to jump up here to 9 inches times W. And then we have no distributed load for 12 inches. So we have no slope. Then I'm going to go downhill with a slope of W, and I think we're going to end up with an anti-symmetric diagram because we have a symmetric beam. We come up here and we would find the area under this. We already calculated it, 18 times W. So after 18 inches, we started at 9W. We're going to end up down at minus 9W. And then we have no distributed load, so we have no slope. And then at the end of the beam, we have By, which brings us back up to 0. And there's our shear force diagram. What's important from this is Vmax. Vmax is equal to 9 inches times W. And we can solve the problem from there. But because it's really good for us, I want to go ahead and just sketch out what the bending moment diagram would look like in case you were ever asked to also find the max bending stress. So what would our bending moment look like? Well, we begin at 0 because there's no couple moment. And we start with a big positive slope of 9W that is constant. So we're going to start with a straight, constant uphill slope until this point. And then our slope is going to start decreasing till it reaches 0. Well, that means we're going on a parabola. And somewhere right there, we're going to reach a 0 slope, and then we switch to a negative slope. So the parabola keeps on going until we reach this point, and then we have a constant slope again, which should bring us back to 0 at the end of the curve. So it's supposed to look symmetric. It may not look perfectly symmetric, but that's the idea. And what we would need if we were solving for max bending stress is we would need to figure out M max, which is going to happen right there at the middle of the beam. And to find it, you would want to come back to your shear force diagram and find that area plus that area. So you'd use area 1 and area 2 to figure out how far up you go. You would have a slope here of 9W, and area 1 would tell you how high that is, and then that little area 2 would give you the rest of the height. So there's a reminder of how we would figure out M max if we needed to find max bending stress. We're going to actually, though, use Vmax. So you remember what our equation was? Tau is VQ over IT. Just figured out an expression for V. I need to find Q, I, and T. So those are all a group of things that we like to call section properties. Our cross section is a nice little rectangle who is 2 inches wide and 8 inches tall. Our thickness is just going to be 2 inches. It's just how thick is the beam. Our moment of inertia, well, this is a rectangle. We want the moment of inertia about its centroid, so we just use 1/12. The base would be 2 inches, and the height would be 8 inches, which gets cubed. Let me calculate that. I get 85.33 inches to the fourth. Now we need to find Q. This problem was asking us to find the W, the max W that you can have before you reach an allowable stress. So we're interested in the max shear stress that will happen wherever Q is max. Q is going to be max and stress is going to be max at the centroid. So I want to take and shade everything above or below the centroid. The equation is y bar prime a prime. So y bar prime is the distance between the centroid of the whole shape and the centroid of your shaded area, which, since the whole shape is 8 inches tall, the half shape would be 4 inches tall, so its centroid would be exactly 2 inches up. So y bar prime is 2 inches, and then a prime is the shaded area, which should be 4 inches by 2 inches. And that comes out to be 16 inches cubed. Now we are ready to plug everything into our equation. The problem told me tau allow. It said tau allow, which I'm going to set equal to tau max, was 400 psi. So let's plug it all in. On the left side, I'm going to have 400 psi, that's pounds per square inch. On the right-hand side, I have V max, which is 9 inches times W. Q is 16 inches cubed. Moment of inertia is 85 1/3 inches to the fourth. And thickness, we figured out, was 2 inches. We need to solve for our unknown, which is W. Let's make sure our units are going to work out. I've got inches cubed over here divided by inches to the fifth. So that's got an inches squared on the bottom, which means inches squared on the bottom cancels inches cubed, inches to the fourth, and inches right there. All those inches are gone. So when I solve this, I'm going to get W in units of pounds per inch when that one comes to the bottom. So W comes out to be 474 pounds per inch. There is our answer if the problem wants it in pounds per inch. I'm pretty sure the solutions manual actually wanted this in pounds per foot. This is a conversion that it seems so simple, but a lot of students will get it wrong. So actually write out the conversion. pounds per inch, I need to convert inches to feet. So I want to multiply this by 1. And I need to make sure that the inches are on the top so it cancels out the inches on the bottom. That way our inches cancel and we'll have this in pounds per foot, 5,690 pounds per foot. Okay, kind of a fun problem. This one did not work us so hard on finding Q max because it was an easy cross section, but we had the difficulty of needing to draw a free body diagram when we didn't even know how big W was, and also sketch out shear force and bending moment diagrams without numbers. What we needed that diagram for, though, was simply to figure out V max. So if you are worried about this beam failing, the spots to be concerned about are here and here if you're worried about it failing in shear. If you're worried about it failing because of bending stress, you'd be actually more interested in the very middle of the beam. Let's do another example. We have a beam with loads on it. We are given an allowable shear stress of 0.25 KSI, and then we're just asked if it will fail in shear, and if not, what is the factor of safety? Very similar process to the last problem. We want to start with a free body diagram. We will need to solve for the reaction forces. Then we will draw a shear force diagram. We'll sketch the bending moment diagram for fun. It's not really needed to solve the problem. Free body diagram up first. I've got downward 4.5 kips. I decided to just switch and make everything pounds. 4,500 pounds. My distributed load acts all the way along here across 8 feet. So I'm going to replace that with a point load at the middle. It's 400 pounds per feet. Uniform distributed load acting over 8 feet. If you multiply that out, you get 3,200 pounds. And then A is a pin, so you could have AX and AY at a pin, but since there are no X forces, AX is equal to 0. Right here, we have BY that's unknown. So we need to do some equilibrium equations next. Equilibrium, I like to sum moments first for a problem like this so that I can solve for something. I summed moments about point A, but you could also sum moments about point B if you want. The only counterclockwise moment will come from BY, and it is 8 feet away from point A. Then we'll have clockwise moments of 3,200 pounds, which should be 4 feet away, halfway along that distributed load, and also 4,500 pounds times 12 feet away. All has to sum to 0. Solving, we get BY comes out to be a positive 8,350 pounds, positive meaning it will act upward. And then if I sum forces in the y direction, I can solve for AY. I have AY plus BY minus 3,200 pounds minus 4,500 pounds. That all equals 0. AY comes out to be minus 650 pounds, or think of it as 650 pounds, but it acts downward. With that information in hand, we can go and draw that shear force diagram. First thing that happens on our diagram is we have AY, which does not act upward, it actually acts downward. So we're going to start by going down to minus 650 pounds. And I'm guessing 650 is fairly small on my scale because I've got a big value of 8,350 caused by BY. First thing is we're going to have a downhill slope of 400. We're going to go down somewhere. How far are we going to go down? Let's go look it up. We're going to go down at 400, an amount equal to the area under the distributed load curve, which I already calculated. We're going to go down a total of 3,200 pounds. So if we're at 650, we go down 3,200, we're actually going to end up down at minus 3,850 pounds. We're going down at a slope of minus 400. Then we reach the point where BY is applied. We jump up 8,350 pounds. We end up at 4,500 pounds. Now we have no distributed load, so we have no slope. And then at the end of the beam, we have a downward 4,500 pound force. So what's Vmax? That's the important thing to come off of this diagram. Absolute value sense, Vmax is 4,500 pounds. And the spot you'd be worried about shear failure is this last segment of the beam where you have that max shear force. Know how big our shear force is, we can figure out how big our max shear stress is, and then go see if it's going to fail, and if not, what is the safety factor. Our equation is tau max is Vmax times Qmax over IT. So we need some section properties. Once again, it is a friendly rectangle, 3.5 inches wide and 14.55 inches tall. So what do we get from our section? The thickness is 3.5 inches. The moment of inertia is 1/12. The base is 3.5 inches. The height is 14.55 inches, which gets cubed, and that number comes out to be 898.4 inches to the fourth. And Qmax Qmax always happens at the centroid, which for a rectangle is in the middle. There is my shaded area. I need y bar prime. That's going to be, oh, I got to do some math. First, I got to find half of 14.55 and then do half again. Oh, that'd just be 14.55 divided by 4. There is my y bar prime. And then my a prime is going to be 14.55 inches divided by 2, so half the height, times 3.5 inches wide. So there is the a prime that goes with the y bar prime. And that q comes out to be 92.62 inches cubed. Let's plug it all into our equation. Tau max is 4,500 pounds with our V max. Q max is 92.62 inches cubed. Moment of inertia is 898.4 inches to the fourth, and the thickness is 3.5 inches. And tau max comes out to be 132 pounds per square inch, or PSI, which is 0.132 KSI. What was tau allow? Tau allow was 0.25 KSI. So this does not fail. And so we need to find our factor of safety. Factor of safety is going to be the allowable, the biggest shear stress you ever want to allow, divided by whatever your max actually is. So we plug in 0.25 KSI on top, we put in 0.132 KSI on the bottom, and we get a safety factor that is 1.85. Bigger than 1, meaning it doesn't fail. Okay, and I promised you guys we would draw that bending moment, so I left myself some space here. Let's draw that bending moment diagram because we should practice it every chance we get. Bending moment diagram right here. What's it going to look like? Well, it's going to start and end at 0 and have no jumps in it because we had absolutely no couple moments applied. It's going to start off with a small negative slope that's going to get bigger in magnitude. So small negative slope of 650 increases in magnitude as we go down, and then we're going to have a straight line all the way back up to 0. How would you find M max? M max is not very hard to find in this case. You can either use the shape on the left, which would be finding the area of this trapezoid, or you could use the area over here of the rectangle. So if I had to find the max bending stress, I'm going to use area 2, which would be 4,500 pounds times 4 feet. M max for this problem would be 4,500 pounds times 4 feet. And then you could go and solve for the max bending stress. To finish this out, I've got a couple of concept questions. First question is, where is the shear stress max? We're assuming that we got an up or down shear because that's all we've been dealing with so far in class. And if I want to know where is the shear stress max, remember shear stress is always max at the centroid of the cross section. So the answer would be point C is where it's max. Next question, where is the shear stress min? Where is the smallest value? The answer is, it's going to be at the top and bottom. So points A and E. Up here at the top, point A, up here at the bottom, point E. Next question is, to find the shear stress at points B and D, what should you use for A prime and Y bar prime? We're looking at finding the shear stress here at B and here at D. So you would think about shading just one of the flanges. So your A prime is going to be the area of a flange, which is 8 inches times half an inch. Well, that's 4 inches squared. And Y bar prime, that's the distance between the centroid of the whole shape and the centroid of the flange itself. Or think about if you start with a reference line here, how far up do you have to go to get to the centroid of that rectangle? It should be 3.25 inches. And picture you might want to draw, looks like this, you're shading in that. So there is your A prime, and Y bar prime goes from the centroid of the whole shape to the centroid of that top flange. So there is Y bar prime. Finally, what is Q for point C? Let's draw another picture again. This time we're going to have two pieces that are contributing to our Q, the purple one and the little green one. Q is going to be, first of all, the Q that we found up above. Q for that purple shape was going to be 3.25 inches times 4 inches squared. Now we need to add to it Q for the green rectangle. Is going to have an area of half an inch times 3 inches. And the Y bar prime is going to be the distance between the centroid of the whole shape C and the centroid of the little green rectangle, which will be 1.5 inches away. 1.5 inches. And then the area we decided was going to be 3 inches times 0.5 inches. For the purple area, this was Y bar prime and this was A prime. For the green shape, this was Y bar prime and this was A prime. You add those all up and you get a number. 15.25 inches cubed. And it should be bigger, than what you would have gotten up here where you're only dealing with the purple area because we just added something else to it. That is as far as we're going to go today in practicing calculating Q and finding maximum shear stress in actual beams, where we need to do the whole problem, the free body diagram, reaction forces, shear force diagrams, find the max shear force, and then finally use our transverse shear equation. Thanks for watching. See you next time.